Okay, so first things first, we need a balanced equation. So sodium phosphate. Phosphate is a -3. Sodium is a +1, so that's sodium phosphate. Copper nitrate. So copper is a +2 charge. Nitrate is a -1, so we're going to need 2 nitrates in that formula. Okay, so double replacement says we're going to combine copper with the phosphate. Now, the phosphate has a charge of -3, which means I need 3 coppers. The copper had a charge of 2, which means I need 2 phosphates. And sodium is +1, nitrate is -1. Let's balance this. I'll start with the copper phosphate. It says I have 2 phosphates, so let's put a 2 over here on the left side. 6 sodiums, 6 over here. And then to get 6 nitrates, I put a 3 here. All right, I have my balanced equation. Checking my solubility rules, I see that the phosphates are insoluble, so this is my solid. That's what's going to be collected. Okay, so now that I have my balanced equation, the answer to these problems is not always going to be the same. It's not always going to be the grams. They can ask whatever they're going to ask, right? But the bridge to get from what they're asking and with the numbers that you have is going to be the mole ratio. That's always the heart of this problem. So let's look and see what they gave us. They gave us the molarity of sodium phosphate. They give us the molarity of the copper 2 nitrate. And then they tell me there's 5 grams of solid precipitate. Okay, so the solid would be this, 5 grams of this. If the sodium phosphate is in excess, right there is a big clue. If they say anything is in excess, that means that's not the limiting reactant. So the limiting reactant is going to be the copper nitrate. How many milliliters of the copper nitrate solution must have been used? So the goal is to find the volume of copper nitrate, but we don't really know anything else about the copper nitrate besides the molarity. So let's take the 5 grams and see what we can get from it. 5 grams of solid precipitate, and we already mentioned the precipitate was copper phosphate. Okay, and like anything, I need to convert to moles. So the molar mass of that is 380.59 grams. So that gives me 0.01314 moles of copper phosphate. Okay, are you guys with me so far? I've balanced the equation and I've turned the mass into moles. Again, they are asking about copper nitrate. So I need to take this value and convert it into copper nitrate. So the mole ratio then is that there's 3 moles of copper nitrate for every 1 mole of the copper phosphate. So effectively, I'm multiplying this number by 3, and that gives me 0.0394 moles of copper nitrate. Okay, now we are at a familiar point because now we have the moles and we have the molarity. When you have moles and you have molarity, you can find volume. Okay, so So 0.0394 moles divided by 0.400 moles per liter gives me 0.0985 liters. And technically they're asking for milliliters, so there's 1,000 milliliters in a liter, so 98.5 milliliters. The last part being the trickiest. Does that make sense now, though? Okay. Okay, so I saw many of you did get that, and so good job on that. So here's a problem. You know, you might look at it, you might first think it's a limiting reactant problem, but it's not. Okay. Find where the question is. Identify what the question is and let that help you figure out what it is you tried to find. When they say how many milliliters of copper nitrate solution, you're solving for a volume. Okay, so in order to find a volume, if they're asking for a volume, that means at some point you're going to have a molarity and moles, because that's the only way you can find for the volume. All right, let's do number 4. Okay, so here they come up and tell you the volume and molarity of 2 different solutions. So again, first things first, balanced equation. So aluminum nitrate, potassium hydroxide, KNO3, and AlOH3. We balance this. I need 3 of these. I need 3 of these. Okay. Check my solubility rules. Hydroxides are insoluble. That's this guy. Okay. It is saying find the amount of solid. Find the amount of solid. Find the theoretical amount of the solid. So this is a classic limiting reactant problem. I'm going to need to find moles first. So 0.02 liters times 0.15 molar, 0.003 moles. Oh, actually, I only have 2 sig figs on that. 0.0030 moles of aluminum nitrate. Okay, and then the other one, 0.035 liters times 0.1 molar, so 0.0035 moles KOH. But those are both of my moles. I am solving for aluminum hydroxide, so my mole ratio now comes into play. It's a 1 to 1, so the number is still 0.003. Okay, now we do the other reactants. I need to cancel potassium hydroxide this time, which has a coefficient of 3. So 3 moles of KOH on the bottom. So this number is going to be divided by 3, which is like 0.00117 moles of AlOH3. Okay. Now we know what our theoretical yield is because that's the lower of the two. And our last step, I guess we could leave it here. It didn't specify what unit. So if you just got here this far, that's fine. I probably will ask on the test for this to be in grams. So we need to go one more step and convert to molar mass. So a mole of aluminum hydroxide weighs 78.1 grams. And so when you multiply 0.091 grams of product. There we go. Ojan.
And ours it says grams.
Good. Then we did it right. Okay. How are we doing? We might be a little out of practice with the limiting reactant thing, although we did do it in gases as well as stoichiometry, right? Okay, so on the solution stoichiometry review sheets, we're not going to get around to assigning them all, but there's lots of extra practice there. If you feel like you need to do more, you can. Okay, if you feel like you've got it, then maybe you don't need to do as many as you think. There is one more type of problem I want to show you, and there's not a prompt here for it. So I'm just going to add a page here so I have more room to write. Okay, we're going to follow through, and we're going to continue on with this problem. So when you see a precipitation reaction like this, and we clearly have identified aluminum hydroxide, there are ions that essentially have done nothing, right? They were aqueous before, and they're aqueous after. Can you guys tell me which ions those might be? Back when we were writing ionic equations, these are the ones that I would have had you cancel out, because they did not end up forming solids. So which ones are we talking about, Nick?
Potassium nitrate.
Right, potassium and nitrate, right. This product here, that's aqueous, but you know what? Earlier, the nitrate and the potassium were aqueous as well. So basically, K plus and NO3 minus, because they were not involved in making a solid, these are what we call spectator ions. And I bring this up because a lot of times we need to know the concentration of everything that's here, including the spectator ions. So this is how we find the concentration of spectator ions, okay? All right, so first step. If you're going to find the concentration of spectator ions, you're going to need the moles of the reactants. And if you're this far in the problem, you already have done this. It was one of the first, in fact, it was the second thing you did in this problem. If I said, find the moles of the compound that contained nitrate. The moles of the compound that has nitrate. How many moles is that? Well, which one am I talking about? I'm talking about aluminum nitrate, right? What are the moles of aluminum nitrate? Right here. Okay, so .003 moles of aluminum nitrate. Now I know that there's two spectator ions. I'm just doing these one at a time. So the next thing, find moles of the ion specifically, meaning I said that nitrate was the spectator ion. Right now, what I have written here is moles of aluminum nitrate. I need to know how many nitrates there are. So, to do that, we're going to use a ratio between the formula and the ion. In one aluminum nitrate compound, how many nitrates are there? 3. And the reason why we do that is because now that tells us that there are 0.009 moles of NO3 minus. That's how many moles of nitrate there were at the beginning. That's how many moles of nitrate there are at the end. And I know this because I know that nitrate did not react. Anything that does not react, its moles does not change. So there's one more step. Find the molarity. Molarity is moles divided by volume. I have the moles now. I just need to know what the volume is. So what's the volume of the test tube now after you have mixed these solutions together? If you mix two test tubes together, their volumes are additive. So what's my total volume? 55, yeah. So it's going to be 0.009 moles over 0.055 liters. 0.16 molar. All right. We said there are two spectator ions. That's one of them. Let's do the other. Find the moles of the compound with the spectator ion. So where are the moles of the compound that contains the potassium? How many moles did we begin this problem with of potassium hydroxide? Right here. Okay, so 0.0035 moles of KOH. But KOH is not the spectator. K is the spectator. So we need to change units. Now I know how many moles of potassium ion there are, and we have one more step. Divide by the volume. These are all in the same test tube, so the volume is the same. It's 0.055. And that is my concentration of the other spectator ion. Okay, anytime you carry out a reaction in solution where you end up forming a precipitate, the spectator ions were floating around before, they're floating around after, but we need to figure out what their concentration is. So you just have to track down how many moles there were of them and then divide by what you know the total volume to be. So even though I wrote out 3 formal steps for this, it's probably more work than it actually is. It looks like more work than it actually is. So let's jump to the second question you did, and let's find the spectator ion. Whoops. Let's go back to the first example that we did, right? Number 3 here. And actually, that's not a good example either. Just kidding. Let's just do this one here. So what I want to know is the following. I want to know how many grams of precipitate can be made, but I also want to know the concentration of spectator ions. So you're going to solve this problem first as it's written, and then when you're done with that, continue on and tell me what the concentrations are of the ions that did not react. Okay? And we'll see if we can get that. So go ahead, take 10, see what you come up with.